Alright, tessellations. If we look at this question here, it says Ellen has bought a box of kite-shaped tiles to decorate part of her bathroom wall. She does not intend to use tiles of any other shape on this part of the wall. A scale drawing of one of the tiles has been drawn on the isometric grid below. Show how it is possible to tessellate the tiles. You should draw at least 7 additional shapes. Okay, so tessellations quite simply means that you're going to join up the same shape. Okay, so you're going to create a pattern on this wall where the shapes join up neatly, they don't overlap, and there's no gaps in between them. So I'll show you now how this particular shape does tessellate. Okay, we can make an exact copy of the shape by the side of it. Alright, so you've got your another one here. Okay, identical shape. That goes to the side of it. Okay, so that would be stuck to the wall. You can do another one by the side of that. And the idea is to stick all these tiles on the wall so that the tiles obviously don't overlap, but there's no gaps as well. You'll notice here there's a gap here that will need filling in, and you might think, well, that tile is not going to fit in here because of course the nature of that side there, the slope of it, there's no way it's going to fit in there. But what you can do with the tiles is you can rotate them around, can't you? You could actually turn that 180 degrees and have the tile going like this. Okay, so you notice there's exactly the same tile there, just upside down. Okay, and the gap has been filled. Do the same here. Alright. Okay, and you can see there's no gaps being left here. So another one upside down there. Okay, and you can keep going. It does say at least 7. I think I've done 5 so far. So we could keep going above. Okay, you want to fill the whole wall. Okay, so you've got one there, upside down, and then we can do one that's normal. Yeah, and you can just keep going like this. And you can see that the whole wall will be filled in. So this shape does indeed tessellate. Okay, in other words, the shapes do not overlap and there's no gaps. Okay, question 2 says show that the given shape tessellates by drawing more of the shapes on the grid below. Again, here you've got, well, you've got here an L shape, haven't you? So we could draw another L shape by the side of it, just like we did in the last question. Okay, keep going like this across the wall. Okay, so there's another L shape. We draw another L shape here. But of course the key to ensuring that they tessellate, or checking that they tessellate, is to show that there's no gaps. Okay, there's no gaps. There's a gap here, isn't there? There's a gap there, there's a gap there. Of course, again, we can, same idea, we can rotate this. Okay, we can rotate the L. So if you notice then, you can have an L that's upside down. Okay. So you've got an L there that's upside down, which fills up the gap. You do the same over here. Okay, you've got an upside down L, same over here. You can see the gap has been filled up. So this L does indeed tessellate. You can keep going, right? You can go underneath, you can draw another L here. Alright, the idea in the exam, if a question like this comes up, is just to prove, you need to prove to the examiner you show that the shape does tessellate. So you do need to keep going, and you do need to add in more of these L's. So you've got an L there, an upside down L of course will fit in there, won't it? Okay. Right, so you just need to keep going like that. So you do another L there, upside down one, right, and then you've got yourself a situation where the shape tessellates. Okay, so there's your L there, and you've got another L there, and so on. Okay. Question 3, it says the tile shown as a rhombus. Explain why tiles identical to the one shown tessellates. You must give a reason for your answer. Okay, well, with a rhombus, of course, there's a video on rhombus, parallelogram, And the idea with that is, with a rhombus, of course, opposite angles are equal, right? Okay, the opposite angles are equal in a rhombus. And the other thing as well, of course, if we know those two there, what's that, 140 and 140, and adds up to 280. Of course, a rhombus is just a quadrilateral, and a quadrilateral, all the angles add up to 360. So if those two add up to 280, 360 take away 280, you're just left with 80, which means then 80 degrees for those two angles. So that's going to be 40, that's going to be 40. Okay, so to show that they tessellate, of course, well, I could draw another one here, another rhombus. Okay. Okay, and in terms of the angles, then we know that's going to be 140. Right? And then, of course, we have this gap to fill in here. Well, you can just put another rhombus here, couldn't you? Right? You could put another rhombus here. Of course, this angle here would be really important. And this angle here would be really important. And we'd need to think, what angle would they need to be? Well, if that's 140, that's 140. Of course, that adds up to 280 as we saw earlier. Angle around this point needs to add up to 360. So if those two add up to 280, we've got 80 left over, which means these two have to be 40. And of course, that's what we have, isn't it, with this rhombus, because they are 40, so we can draw more rhombuses. Okay, and you can see clearly then that this shape will indeed tessellate. Okay. Question 4. So the idea of tessellations, obviously connected to polygons, right? So again, there's a video on polygons, but part A here says calculate the size of an interior angle in a regular 12-sided polygon. But remember, however many sides it's got, you can split it up into triangles, can't you? And it's always 2 less, isn't it? So if it's got 12 sides, that means you can split it up into 10 triangles. Okay, so the shape 12-sided inside, then you can split it up into 10 triangles. Now, in each triangle is 180 degrees, so we've got 10 triangles, 10 lots of 180 degrees is 1,800 degrees. So to get one of, this is, of course, this is all the angles, the sum of all angles, all interior angles. To get one angle, well, of course, because there's 12 sides, it's going to be 12 interior angles, so you need to split that into 12. Okay, so use the bus stop method. 12 into 18 goes once with 6 remainder. Excuse me. 12 into 60 goes 5 times with no remainder, and 12 into 0 goes 0 times. So that's 150 degrees. That's the interior angle. Part B then says, do regular 12-sided polygons tessellate? You must give a reason for your answer. Now think about the angle here we've got, right? The interior angle of this this 12-sided polygon is 150 degrees. So if it was to tessellate, okay, so in other words, you'd put another 12-sided next to it, well then you'd get another 150 degrees here, wouldn't you? Okay, we'd be able to do that, wouldn't we? There's nothing wrong with that, because that will fit in nicely. If you've got 150 degrees here, 150 degrees here, so we'd have to think, now, well, what's left here is, are we going to fit another 150 degrees in here? Now you might think, the way I've drawn this, you might think, well, yeah, it looks as though you could fit in 150 degrees, okay? But of course, you can't go by looks here, because I've just drawn this without, I haven't drawn it to scale, haven't I? I haven't measured that out. Okay, but if that's 150, that's 150. Can we fit another 150 in here so they join up nicely, so there's no overlaps, no gaps? Well, if there was 150 here, okay, it's not going to work, isn't it? Because in the circle, it adds up to 360. Okay, so 150 and 150 for those two, that comes to 300, which means there's only 60 degrees left here. Okay, so obviously we're not going to be able to fit another 12-sided in here, alright? So in this case it's not going to tessellate, alright? So we say it won't tessellate. Okay, because when you put two together, the total angle is 300 degrees, and there will be a 60-degree gap, which will be impossible to fill, won't it? Will be impossible to fill. Okay.